steps are pretty much the same. So the problem you're given in number 16 is something like, you're given some integrals. So like the integral from 2 to 7 of a function is 3. The integral from 2 to 13 of a function is 20. And the integral from 10 to 13 of a function is equal to 5. And the question you're asked is to find the integral from 7 to 10 of that function. And so the main thing at play here is that if you're integrating a function or finding the area of a function, you can break that up into many sub-integrals. So like if I want to find the area from A to B, the area under the curve from A to B, so the integral from A to B of f of x, I can break that up anywhere in between and say it's the integral from A to C of f of x, which is the area here in blue, plus the integral from C to B of f of x, which is the area here in red. And that's going to be the total area. Blue plus red is going to equal green. I didn't have purple. I would have used purple if I had purple, because blue and red make purple. But you can totally see that you can break up an integral at any point. Actually, at any point. It doesn't have to actually technically be between A and B, although it makes more sense visually between A and B. But you can technically break up an integral at any point you want that's outside of the integral, which is kind of weird, but we can talk more about that later if you want. So what I really want to think about here is kind of the biggest region I'm given. I'm given this, the integral from 2 to 13. And so I'm going to, in fact, I'm going to erase this right here. We're trying to find the integral from 7 to 10. So I want to know, right, what's the integral from 7 to 10 of x dx? And what I can think about doing is using a different color pen, is breaking up the regions I've got. So I've got from 2 to 7. I'm looking for from 7 to 10. I've got from 10 to 13. And here's what I know. I know that the area from 2 to 7 under the curve is 3. I know that the area under the curve from 7 to 10 is what I'm trying to find. I know the area from under the curve from 10 to 13 is 5. And the total area from 2 to 13 is equal to 20. So I can see that 3 plus the thing I'm trying to find plus 5 is equal to 20. So that the thing I'm trying to find is equal to 12. That is definitely one way you could tackle it. Yeah, 12, exactly. Another way you could get there without drawing this picture, although I think drawing the picture is a really good idea. Another way to get there is to say, okay, and really I'm just going to do the same thing, but without drawing the picture. Oh, sorry, there's someone. Is my volume not on? Sorry, I didn't hear someone trying to come in. Sorry, if you've been saying words and I didn't hear you, it's because my volume was accidentally off. So if you ever say something and I haven't responded to it, I'm not ignoring you. It's because I forgot to turn my volume on. So if you're saying words and I'm not hearing you or responding, you should type something in the chat so that I can see that you say, James, your volume is probably off. Because I will not ignore you if you say words. So what we could also do here is say that that integral, right, the integral from 2 to 13 of f of x is equal to, we can just break it up. It's the integral from 2 to 7 of f of x plus the integral from 7 to 10 of f of x. I should write my dx's plus the integral from 10 to 13 of f of x. We know that this is 20. We know that this is 3. We know that this is what we're trying to find. And we know that this is 5. So really it's the same work, right? You're going to get the thing you're trying to find is still 12. This idea is important, that you can break up an integral at any point in the interval, actually any point really. So I want to erase some of this because I want to say one more quick thing here. Let me erase this, yeah. So it is certainly true that, sorry, I got too many pens. The integral from a to b of f of x dx can be broken up at any point between a and b. So it's the integral from a to c of f of x dx plus the integral from c to b of f of x dx. I know I literally just wrote down the same thing I erased, but here's the difference. C doesn't actually have to be between A and B. It makes the most sense in my mind if it does, but it totally works if it isn't. So let me draw you a picture. So here's our function, f of x. Here's A, here's B, and here's C, outside of A and B. And what I'm saying is, even though I'm thinking about kind of taking the integral from A to B of f of x, which is just the area under this curve, right? So that's this part right here. Here's what we're going to say, and this might seem kind of strange at first. It is actually correct to say that this is equal to the integral from A to C. So I'm gonna try and do this part in red here. So the integral from A to C is all of this. I should do it the other way, sorry. It's all of this. There's my integral from A to C. Plus, that seems weird, the integral from C to B. Now here's the thing. The integral from C to B, those limits of integration are out of order. So this is really equal to the negative of the integral from B to C of f of x dx. And then I can add this to the other side, and it totally makes sense. The integral from A to B plus, when I bring this over, the integral from B to C is equal to the integral from A to C. Yeah, it's super smart. But so here's what it means. It means that if you've got an integral from A to B and you want to break it up at some point that's convenient, you can pick any number that doesn't have to actually be between A and B, as long as it's in the domain of the function. So for example, I'm trying to think of a good example now. I don't really have a, if I was trying to calculate, like the integral from, I don't know, I don't really have a good example. I'm just going to make something up that's not super great. Let's say I was doing like the integral from, I don't know, 1 to 3 of 10 minus x quantity squared. And for some reason, I decided it'd be a good reason to break it up at 10. I totally could, although it seems weird to break it up, write it as the integral from 1 to 10 of 10 minus x squared dx plus the integral from 10 to 3 of 10 minus x squared dx. Perfectly legitimate. Kind of weird. Okay. And again, I will say, you can pick any point as long as it's in the domain of the original function. And 10 minus x squared domain is everything, so we're fine. Okay, so let's look at some other questions people had before we start getting to the use of stuff. People had a couple questions about some fundamental theorem of calculus stuff. So I came up with a couple questions that are similar to questions, I think 33 and 34 on the web work. Or is it WebAssign? I don't know, it doesn't matter. Web work, I think. So let's look at this first one here. So this first one says, this is similar to problem 33. G of x is equal to the integral from 3 to 1 over x squared of arc sine of t dt. This is a very kind of just classic, regular, fundamental theorem of calculus problem, where we're going to take the derivative of this, just like we were doing last class on Tuesday, right? By plugging in this for every t, but then also multiplying by the derivative of it. So g prime of x here is going to be arc sine of 1 over x squared, and then I'm going to multiply by the derivative of 1 over x squared. So I'm going to rewrite 1 over x squared as x to the minus 2, so that then it's easier for me to differentiate it, and the derivative of that is negative 2 times x to the negative third. So I could totally write this as arc sine of 1 over x squared times negative 2 times x to the negative third. I would probably rewrite it just because I like to rewrite things. I would probably put this in front because it's not in the arc sine function. I would probably write this as negative 2 over x cubed times the arc sine of 1 over x squared. So that would be the derivative of this function, right? Because when you take the derivative of an integral, you get back the function you started with. It's just in this case, the inner function is more complicated than just x. So we have to use the chain rule and multiply by the derivative of the inner function, which is negative 2x to the negative third, or negative 2 over x cubed. Questions about this one? That reminds me. So let's look at the next one I have on the board here, which is definitely more complicated. This is like problem 34 on the web work. And it actually took me a minute to like actually think through how it works. So here's what they're giving you. They're giving you capital F of x is the integral from some constant to x of f of t dt. And they're also giving you that f of t is equal to the integral from 2 to some function of t, right? It's not just t, but it's t cubed in my problem. So the integral from 2 to t cubed of some function of u, right? The square root of 1 plus u to the fourth over u du. And then they're asking me to find capital F double prime of 3. And before I'm going to think about plugging in a 3, I'm going to write f double prime of x. And then plug in 3 for x after I take a derivative, right? You can't plug in a constant to a derivative until after you found what the derivative is. Otherwise, you just get 0 if you plug in a constant and then differentiate. So to find the second derivative, I got to start with the first derivative. So you guys, everybody should be able to tell me, looking at this integral here, where capital F of x is equal to the integral from 2 to x of little f of t dt, what's the derivative of this? What is capital F prime of x going to be? Fundamental theorem of calculus. Exactly. It is just f of x. Excellent. And I try to avoid using the words cancel out, but yes, I would say that the derivative undoes the antiderivative. And cancel is not so bad. There are other things where I'm more against canceling. Cancel is probably fine here. And so then if I want to find f double prime of x, well, the derivative of this is equal to the derivative of x. That's going to be little f prime of x. So really, this was a very kind of convoluted way to just ask you to take the derivative of this. So we know how to take the derivative of this. You plug in your thing, and then you multiply by the derivative of the thing. So here's what I know. I kind of want to use this side of the board. So I know that f prime of t, I'm just taking the derivative here just like I did for this problem over here, right? I'm going to plug in the t cubed for every instance of my variable u. So I'm going to get the square root of 1 plus t cubed to the fourth over t cubed. And then what do I have to multiply by out here? Very good. You're very close, Jason. You're missing a power, though. It should be 3t squared, right? Yeah, the derivative of t cubed. Okay, that's f prime of t. So that's also f prime of x, right? I mean, it's the same thing. You can write f prime of x as square root of 1 plus x to the third to the fourth over x cubed times 3x squared. It doesn't matter if you use t's or x's. So then we can find f double prime of, I don't remember what I asked for. I think I said f double prime of 3. 3 seems like a really big number at this point. Sure, we can do f prime of 3. It's going to be kind of stupidly big. Oh well. F double prime of 3 is just little f prime of 3, which is just this thing here with a 3 plugged in for every t. So I'm going to get the square root of 1 plus t to the third to the fourth is t to the 12th, so 3 to the 12th, which is too big, over 3 to the third times 3 squared. These end up canceling each other out, right? 3 times 9 is 27, 3 to the third is 27. So we just get the square root of 1 plus 3 to the 12th, which is really pretty large. I mean, it's not that big, but it's pretty big. So I would probably leave my answer like this. It should be fine for web work or web design. if your answer is kind of like written as a square root of some large-ish number. But that's how you do a problem like this. If you're asked for the second derivative, you need to go derivative by derivative. So we found the first derivative by using the fundamental theorem of calculus here. We got f of x, and then we found the second derivative by taking the derivative of x by using the fundamental theorem of calculus here. So that's how that problem kind of works. Before we look at the other ones you asked about, Rodrigo, which were definitely a little bit harder for u substitution, I feel like we should kind of go through some more basic u substitution problems, because u substitution is definitely, u substitution is a process you are all going to use a lot. Eventually, once we start learning about other methods, you'll be like, oh, thank God this problem is a u substitution, because u substitution is like the easiest method that we have for anti-differentiating something. So we're going to be happy to see u sub problems in the future. They're going to be like, oh yeah, this is our easy stuff compared to the other methods of integration we're going to learn later. So, yeah, and there really are a couple ways to go here, because we can talk about u substitution in the context of integration of indefinite and definite intervals. And I feel like it makes more sense to start with indefinite, but we'll definitely get to the definite ones. We'll definitely get to the definite ones, yeah, soon here. Let me just grab one thing. Where'd you go? Sure, okay. Yeah, that's not what I want. That's what I want. Okay, let's take a look at all this. Yeah, okay. So as I was saying last class, and hopefully your teachers have also said this. I feel like I'm sorry. I feel like there's something I'm forgetting. Oh, I know what it was. Yeah, sorry. Let me just take a. Let me make this bigger. Yeah, cool. All right. So, again, let me reiterate that when you're thinking you might be wanting to do a u substitution for your integral, you're trying to find a choice for u that has it so that the derivative of that choice is also in your integral. So for example, we could look at the integral of x squared times the square root of 1 plus x cubed. And unlike some previous examples we might have done, this one, you can't really, what's the word I'm looking for? You couldn't simplify this, right? In the previous example we did at the end of last class, we kind of like multiplied the thing out and then said, well, you could multiply it out or you could do a u sub, and that was fine. Here, that's not an option. We can't multiply this out. There is no simplifying this. Our only possible plan of attack here is to do a u substitution. So that's what we're going to do. And we're going to make the choice to let u equals. Now, we actually have a couple choices. Should we let u equal x cubed, or should we let u equal 1 plus x cubed? Either way, the derivative is going to be 3x squared. Which of those seems like the better choice? Well, here's what's almost always true. Sometimes it's not true. There are some weird inverse trig examples where you don't want to make the larger choice. But typically, if you can pick u to be a thing or u to be a thing plus a constant, you usually want to grab that constant because it's going to make your transformed integral a little bit simpler. And it's not going to cost you anything as far as complexity when you find the derivative of u. So I'm going to make this choice, not this choice. And I'm making this choice because one, this thing, 1 plus x cubed, is stuck inside this integral. Or sorry, inside this square root here, right? We are usually guessing our u is going to be something that is stuck inside some other function. And that could be inside a square root, or any kind of root, or in the denominator, or in a trig function, or in an exponent, or in any place where it's not just in like the, I don't know what you call like the regular part of an expression, but it's not just something you could easily. The other important reason we are choosing this to be our u is because the derivative, du dx, is also in our integral. Well, I should be a little bit more specific, right? We have x squared in our integrand, and this is a 3x squared. We can always adjust for a constant multiple. So I'm really just picking 1 plus x cubed because I know the derivative has something times x squared, and I have an x squared here. I don't care if I have the right constant. It'd be nice, like I'm not gonna lie. It would be great if there was a 3x squared up there, but there isn't, and I can fix that just fine. So as long as we are only off by a constant multiple, it is always fixable. So here's how I'm going to do this. I'm going to rewrite this as, I'm going to multiply both sides by 1/3. So 1/3 du equals x squared dx. Again, there are usually multiple ways of doing this kind of part. You should do it whatever way you think is best, but this is the way I like to do it. So I see the following. I see that my integral has an x squared dx, right? I'm going to take that x squared dx and I'm going to replace it with a 1/3 du. And I really, really, really want to strongly emphasize here, it is in your best interest to transform whatever has the dx part into the du part. We always have to make sure dx turns into du before we do anything else. So here's what we've got. We've got the integral of x squared times dx is 1/3 du. And I like to write it at the end because we usually, at least in our way of writing integrals, we write du at the end. It's interesting, actually in different languages, the way they express integrals can be different. Like sometimes, definitely I've seen languages where you write the du part first, which kind of makes sense because you're saying like, this is the variable I want to integrate with respect to. So there are different ways of writing integrals, which can be confusing. We write the du at the end, or the dx at the end. And then I still have this part left. Well, this part here, that is my u. So this is going to be the square root of u. And now before I anti-differentiate, I'm going to do two things. Something I'm always going to do before I anti-differentiate is write any root as a power, right? We almost never anti-differentiate roots as is, or we always at least think of them as powers. The other thing I'm going to do is I'm going to factor out any constant multiples. So I'm going to write this as 1/3 times the integral of u to the 1/2 du. And then I'm going to do the antiderivative. So the antiderivative of u to the 1/2 is u to the 1/2 plus 1 divided by 1/2 plus 1 plus c. I'm going to simplify. It's going to be 1/3 times, I'm going to leave myself some space. 1/2 plus 1 is 3/2. And dividing by 1/2 plus 1, or dividing by 3/2 is the same as multiplying by the reciprocal, which is 2/3. So I end up with 2/9 times u to the 3/2 plus c. And then I can finally plug back in that u is equal to 1 plus x cubed. So that my final answer is 2/9 times 1 plus x cubed to the 3/2 plus c. I will point out, because I think it's worth pointing out, if you had to do this as a definite integral, so like if someone said, find the integral from 0 to 2 of this function, you could just do it like a definite integral the whole way through, do the substitution, and then after you plug back in what x is, then you can say, okay, well, the integral from 0 to 2 of x squared times the square root of 1 plus x cubed dx is equal to that thing I found. I don't need the plus c. So I get 2/9 times 1 plus x cubed to the 3/2, evaluated between 0 and 2. That is definitely one way you could do a definite integral, is you could just do it as an indefinite integral, and then at the very end, plug in your limits of integration. If that's what I did, I would end up with, sorry, I'm kind of running out of room here. 2/9 times, I plug in 2, I get 1 plus 8, which is 9 to the 3/2. Minus if I plug in 0, I get 1 to the 3/2. That would end up being 2/9 times 9 to the 3/2 is 27, 1 to the 3/2 is 1. So 27 minus 1 is 26. This would end up being 52 over 9 if it was a definite integral. Also notice, indefinite integral, answer is a function of the variable that we started with. Definite integral, answer is a number. It's the amount of area under the curve between those 2 points. So very, very clear distinction there. Okay, let's do more examples. So let's look at, what do we got here? Sure, let's look at that. How about the integral of tangent cubed x secant squared x dx? This problem, we have choices. What is one potential choice for you? Ooh, let me tell you guys what isn't a choice for you. And so this is actually going to be, so when we start talking about integration by parts later on, we're going to use u as well because someone made a bad choice way back when. Yeah, I'll answer that question in just a second, Sophia. So later on in integration by parts, we're going to pick a u and a dv, and it'll be perfectly fine for u to equal x. When you're doing a u substitution, it's never good for u to be x. Because if you let u equal x, you're just changing your letters from x's to u's. Because if u is x, then du dx is 1, so du equals dx. And you literally just say, okay, well, it's tangent cubed of u, secant squared of u, du. You haven't helped yourself. So good question, Sophia. What are we looking for in a u? We're looking for something that is stuck inside another function, which you could totally think of this as the integral of tangent of x quantity cubed times secant of x quantity squared. And you're also looking for a u whose derivative is also in the integral. So can you pick anything in here whose derivative is also there? We definitely can. Yeah, we can pick tangent. If u is tangent, our derivative du dx is secant squared x. And du is equal to secant squared x dx. And that's great because we exactly have that. That's like the best case scenario. There's our du right there. So we can rewrite this integral. Oops, sorry, I forgot the dx over here. That's terrible. It's always important to write your dx's. So we can rewrite this integral as the integral of something du. And what's the something going to be here? Anybody? Yeah, exactly. It's going to be u cubed. So then we get the antiderivative of u to the third, which is u to the fourth over 4 plus c. And then we plug back in u, which is tangent, and we get tangent of x to the fourth, or as we usually write, tangent to the fourth of x over 4 plus c. And that's it. Not too terrible. So again, definitely I can explain the steps. See, now let me go grab another example here because I definitely had a couple good ones here. 1 second. Sure, let's look at this. So let's look at this next example. The integral of x to the fourth times x to the fifth plus 2 to the 7th power. And while it is certainly possible to multiply this one out, and I've actually had students multiply this one out on a test, it was nobody's idea of a good time. You don't want to multiply this out, right? Our goal for a lot of mathematics isn't just to do it right, but to do it so it's not terrible, right? We want to make this easy for ourselves, or as easy as possible. So I'm going to choose something for you. And again, there are 2 things informing my choice. One, u is stuck somewhere. It's being raised to a power. It's in an exponent. It's in a root. It's in a trig function. It's in some other function. Here, x to the 5th plus 2 is in the function of being raised to the 7th power. The second thing we're thinking of is the derivative of u, du dx, should also be there in our integral. This isn't always going to be true for us. There are going to be some u substitutions where this doesn't work out so nicely and we have to like work harder. Those often are ones where we have to do what's called a back substitution or a power substitution. But ideally, we would love for both of these things to be true. The first one also is just kind of more of a way of thinking about what we might pick for u. It's not a hard and fast rule. So now I'm going to pick u equal to x to the 5th plus 2. My derivative, is that a dx or a 2x? I'm assuming, right there, that's a dx, yeah. If it's at the end of my integral, it should be a dx, but I can see how you might think that looks like a 2. I don't blame you at all. My d's get a little sloppy there. That's a little bit better of a d. No problem. So my du dx is 5x to the 4th. As far as we're concerned, that's good enough. I have an x to the 4th, 5x to the 4th can be modified. So I'm going to rewrite this as du divided by 5 equal to x to the 4th dx. You don't need to rewrite your integral, but you certainly can rewrite it so that these pieces are next to each other. Right? I could totally rewrite this as the integral of x to the 5th plus 2 to the 7th times x to the 4th dx. You don't need to do that, but you can. And then this is my 1/5 du, or du divided by 5, either way you want to think of it. This here, that's my u. So I'm going to rewrite this as, I always like to bring my constant multiples out to the front. So I'm going to write this as 1/5 times the integral of u to the 7th du. Right? It was going to be the integral of u to the 7th times 1/5 du, but I brought the multiple of 1/5 out in front. It's perfectly fine. And then we just do the normal thing. We anti-differentiate. We get 1/5 u to the 8th over 8 plus c, and then we simplify. I replace u with what I said it was equal to, which is x to the 5th plus 2. This is going to be x to the 5th plus 2 to the 8th over 5 times 8 is 40 plus c. Okay. I feel like, let me look for something real quick here. I definitely feel like the problems I've looked at on WebWork seem kind of more bizarre than a lot of these. Let me just, I've got a bunch of things up here. Let me look real quick. Yeah, that one. Let me go back this way. That's fine. Sure, that seems like something we could look at. There was another one too. Yeah, okay, cool. So let's look at something like, on the last few steps. Sure. So let me open this door. I think my cat wants to get out. Let me give her a chance to get out here. So the last two steps. So you're talking about right here? Yes, okay. So what we did was we actually did the antiderivative. Right? The antiderivative of u to the 7th, I'm just using the power rule, or what I call the anti-power rule, right? Where we take our thing to a power, we add 1 to the power, and we divide by the new power. That's how we anti-differentiate anything to a power. So I got u to the 7 plus 1 divided by 7 plus 1. And I still have this 1/5 coefficient out here. And then after that, I just simplified. So the denominator, 5 times 8 is 40. The numerator is u to the 8th, but I have to plug back in what u is equal to, right? Because if we're integrating a function of x, we should end up with a function of x. So when you have an indefinite integral, you have to end, your answer has to be using the same variables that you started with. For a definite integral, it doesn't matter really because eventually we're just going to get a number anyway. Yeah, let's look at this example here. Oh, I know what I want to say later. There's so many things to say. Okay, so let's look at this example. So yeah, I think it's time we start talking about these in the context of definite intervals. So let's do a definite integral, and we'll talk about the different ways we can go. I've got a good example ready to go already. Let me just see where it is. Where'd you go? Yeah, let's do that one. Okay, sure. So let's say I want to do the integral from 0 to 2 of 6x squared over 1 plus x cubed to the 4th. Or you might see someone write this as the integral from 0 to 2 of 6x squared times 1 plus x cubed to the negative 4th. Right? They're the same thing, just written slightly differently. Okay, so as a point, or as a, yeah, these are the x values, right? We're saying I want to find the area under the function f of x equal to 6x squared over 1 plus x cubed to the 4th between x equals 0 and x equals 2. Great. So we can go two different directions here. Either way, we're going to do a u sub. So the u sub is going to be, the obvious choice to me seems like it's 1 plus x cubed, because the derivative is 3x squared. And depending on how you want to do this, you could either say, I don't know, I might do it this way. I might say multiply both sides by 2. So I have 2 du equals 2 times 3 is 6x squared dx. Right? Because I see that I have a 6x squared dx. Or you could have said du divided by 3 equals x squared dx. Either way, it would end up working out. Okay, so one option is to rewrite it this way. Is to rewrite it as, okay, my 6x squared is 2 du over u to the 4th. I don't really like writing the du in the numerator like that, but it's fine. Lots of people do it. I kind of prefer to write it out to the side. So I would rather write this as 2 over u to the 4th du. And you notice I didn't write my limits of integration. I think it's kind of wrong to not write them, but some people really don't want to change them. So you can either not write them, or you can say my limits of integration are still x values. X equal to 0 and x equal to 2. The reason I'm writing that down is to remind myself that those are not what u is equal to. So when I get down to the end after I do the antiderivative here, I can't just plug in 2 for u and 0 for u. Watch. So this is going to be, so I'm going to anti-differentiate this. I'm going to write it as the, I got it from here, the integral from x equals 0 to x equals 2 of 2u to the negative 4th du. And then I'm going to anti-differentiate using the anti-power rule. So I'm going to get 2u to the negative 4 plus 1 is negative 3. You know what? I made a dumb, no, that's fine. I'm sorry. Yeah. Oh, no, I actually see the real smartness of this choice. So 2u to the negative 3 divided by negative 3. Evaluated between x equals 0 and x equals 2. And then I'm going to rewrite this so it's a little bit easier to work with. I'm going to write this as negative 2/3 times 1 over u cubed from x equal to 0 to x equal to 2. And I really want to point out here, even if I wanted to plug in 0 for x or 0 for u, I couldn't. 1 over 0 cubed is undefined. So I can't plug in 2 for u and 0 for u because those aren't the u values, those are the x values. So what I have to do if I'm doing it this way, where I'm not changing my limits of integration, I then have to go back to what u is equal to in terms of x. So I have to rewrite this as negative 2/3 times 1 over 1 plus x cubed. Right? I plugged in u. So now I have 1 over u cubed, which is 1 over 1 plus x cubed from 0 to 2. And now, and those are the x values. That's x equals 0 to x equals 2. And now I can plug those in and get negative 2/3 times, if I plug in 2, I get 1 over 1 plus 2 cubed is 8. 1 plus 8 is 9. So I get times 1 over 9 cubed. And then minus negative 2/3 times, if I plug in 0, I get 1 over 1. So just that. Okay. I don't really want to simplify it anymore because it's not really important. In the denominator, 1 plus x to the third to the fourth in green. Yeah, that's a 1 plus x to the third to the fourth. Is it kind of hard to see? I feel like sometimes the green pen doesn't show up so great. Yeah, it's 1 plus x cubed to the fourth. Okay, so now we're going to do it again, but we're going to do it different. Let's not use the green pen. So the other way we can go is by so we're still making the same u substitution. I'm still going to get the same integral of 2 over u to the fourth du. But now I'm going to change my limits of integration so that, okay, I'm going to use this equation and say, all right, I know the lower limit was x equal to 0. If x is equal to 0 and u is equal to 1 plus x cubed, then u is equal to 1 plus 0 cubed, which is just 1. So the lower limit is u equal to 1. And similarly, if x is equal to 2 at the top, u is equal to 1 plus x cubed, so u is equal to 1 plus 2 cubed, which is 1 plus 8, which is 9. And those are u values. So now, after we anti-differentiate, we don't have to change back to the variable x. We can just plug in u equal to 9 and u equal to 1. So we're going to get the same thing, right? We anti-differentiate this. We already know the antiderivative is this, where we did the antiderivative already. This is going to be negative 2/3 times 1 over u cubed from 1 to 9. But now I don't change back to x. I just plug in the 9. I get negative 2/3 times 1 over 9 cubed minus, and then I plug in the 1. And I get negative 2/3 times 1 over 1 cubed, which is just 1. And look, our answers are exactly the same. Personally, I prefer to do it the second way. I like changing the limits of integration. I feel like it's less messy at the end to have to go back and plug in what the x's were and then plug in the limits of integration that were the x's. But either way is valid. So if you really prefer to not change your limits of integration to u values, that is also perfectly fine. So that said, let's look at some more examples. Where'd you go? I had one right there. Yeah. So let's look at something else. This is similar to a question that was emailed to me. I want to find the integral from, I don't know, let's say the integral from -6 to 0 of x minus 4 to the, how terrible do you want to make this? Let's go to the third. That seems, yeah, that seems all right. I think it won't be too terrible. Sometimes the numbers are curves, that's just life. Okay, I will mention again, as I will often mention, if you really wanted to, you could totally just multiply this one out. I don't think you should, but you could. X minus 4 cubed is x cubed. No, I don't care, it doesn't matter. It's x cubed minus, no, stop. Okay, so we're gonna let u equal x minus 4 because it's the thing that's stuck inside another function. And its derivative, sure. Whenever you're letting u equal just x plus or minus something, or a multiple of x plus or minus something, your derivative is already there. And here, my derivative, my du dx, is just 1. So du is dx. That's like the easiest case ever. Dx just becomes du. So we're going to rewrite this integral as, ow, that stupid chair, get out of the way. Okay, we're writing this integral as, so dx is just du. Choose some different colors here. And clearly x minus 4 is u. So we're going to be integrating u to the third du. All right. So help me out. I know that u is equal to x minus 4. If x is equal to 0, what should u equal? Thank you. And somebody else, if x is equal to negative 6, what's u going to equal? Yeah. Thank you, Kimberly and Rodrigo. So make sure you get them in the right order. And I will also point out, I don't know, I'll do a different problem. Sometimes they have to match, right? So if 0 is on top, the corresponding value should go on top. If negative 6 is on the bottom, negative 10 is on the bottom. Sometimes when you do u substitution, you end up getting your limits of integration out of order because of how things work. That's fine. That just happens sometimes. Okay, and again, these are u values. So now we're just going to integrate. We're going to get u to the 4th over 4 from negative 10 to negative 4. And we're just going to plug those in because those are what the u values are equal to. So I'm going to plug in u equals negative 4 and get negative 4 to the 4th over 4. I'm plugging in negative 10, get negative 10 to the 4th over 4. This is actually not too terrible to simplify. Yeah. So this is going to be, let's see, negative 4 to the 4th is going to be positive, right? Because it's to an even power. So that's going to be 4 to the 4th over 4, which is 4 cubed, which is 64. And negative 4 to the 4th is 256. And if you divide that by 4, you get 64. And then, sorry, minus negative 10 to the 4th is 10,000. 10,000 divided by 4 is 2,500. So I end up with a negative answer, which is okay. We get negative 2,436. Which does make sense because if you graph this thing, x minus 4 to the 3rd from negative 6 to 0, right? Negative 4, right? You're like, it's super light. Right, this function does something like this, where this is 4, this is 0, this is negative 6. So we're looking at like this region down here where the area is clearly a negative area. Don't worry too much if your area is negative. That just happens sometimes. Or if I should say your integral is negative, right? Because area technically is always a positive value. Yeah, that's a good problem. Let's look at some more examples. Yeah, we should do one like that. Totally. We do one like that too. Okay. So this problem, darn it, just went away. There you go. Oh yeah, I know what I was gonna do. Yeah. Let me think for a second here. Yeah, let's do integral from. Yeah, we could do that. That's not terrible. Let's do the integral from 2 to 3 of x times the square root of 3 minus x dx. Okay. So it looks kind of terrible. Typically, when you have square roots of things added or subtracted together, that's problematic. You can't simplify that. We almost always have to let u be the thing that's inside the root. So we're going to let u equal 3 minus x. And here du, the derivative, so I've been writing du dx every time and then bringing the dx over. Typically what we actually do is we just say the derivative of this is what it is. Derivative of 3 minus x is -1. And then we immediately just pop over the dx. So the du is equal to -1 dx, or just negative dx. So the negative du is equal to just positive dx. So we're going to start replacing things. That's going to be du. Sorry, negative du. I'm probably going to bring the negative out in front. That's the way I typically roll. Sorry, my chair is too much in the way. Where's my cat? I thought she was still in here. Maybe she didn't. Maybe she. Sorry, it's been a weird cat day. Okay, and then 3 minus x is u. If x is 2, right, u is going to be 3 minus 2, which is 1. And up here, if x is 3, u is going to be 3 minus 3, which is 0. And I've done the job of transforming everything into u's, except for this x here. Right, here's what I've got. I've got the integral from u equals 1 to u equals 0. Oh, look, here's that thing happening that I said might happen where the limits of integration are kind of out of order of the normal way. That's fine. That's something that happens. And then I've got this x thing here, which I'm going to deal with in a minute, times the square root of u times negative du. Okay. Does anybody know what x is? I mean, it's kind of on the board somewhere already. Does anybody know what x is now? Or could you solve for x? Yeah, totally. You might see. So this is what's called a back substitution. You took care of the dx du part. You took care of the part that you said was u, but then there were leftover x's. And if there are leftover x's, we take our choice for u, we solve for x, and we back substitute in for the remaining x's. And yes, x is 3 minus u. Right, if I solve for x, I add x, I subtract u. Okay. So here's a nice thing that I have noticed. Sorry, there's some parentheses around there. I'm going to factor out this minus sign because I can, right? Just like I factored out the 1/5 in the previous problem, whatever the multiple of du is can always come out in front of the integral. So I'm going to have minus the integral from 1 to 0 of 3 minus u times the square root of u, which is u to the 1/2. And now a really nice thing happens, and this happens a lot. These are out of order, but I have a minus sign. And if I want to change the order, that's going to make it a negative. But a negative of a negative is a positive. So I can totally get this the way I want it to be and eliminate the negative sign all in one fell swoop. I get positive integral from 0 to 1. And then for my integrand, I have to distribute this u to the 1/2 before I can integrate. I want to make this extra super specially clear. You cannot integrate a product of things or a quotient of things by just integrating each part and multiplying the result. I've definitely seen people, not any of you specifically, but I've definitely seen people say that the integral is 3u minus u squared over 2 times u to the 3/2 over 3/2. Right? They integrated this, and they multiplied the results together. No, don't do that. It is so wrong. And the reason it's so wrong is because of the fundamental theorem of calculus, right? If this were the antiderivative, then the derivative of this would equal this. But to take the derivative of this, you would have to use the product rule. it wouldn't just be the derivative of this times the derivative of this. It'd be the derivative of this times this plus the derivative of this times this, which isn't that. So don't make that very easy error, right? Don't integrate a product of things by integrating each factor. Instead, we do the smart thing. We multiply it out and then integrate. Right? This is going to be 3 times u to the 1/2 minus u to the 1 times u to the 1/2. We add those powers, and 1 plus 1/2 is 3/2. And now, finally, we can anti-differentiate. We get 3 times, so here's the way I usually do it. I know that 1/2 plus 1 is going to be 3/2. So I'm going to get u to the 3/2. And then I'm going to multiply by the reciprocal of that power. So I'm going to divide by 3/2, which is like multiplying by 2/3. And then the 3's will cancel there. And then I get minus u to the 5/2. I didn't leave myself enough room like I said I was going to. Dividing by 5/2 is like multiplying by 2/5. From 0 to 1. So then finally, need some room over here. We plug in 1, and we get 2 times 1 to the 3/2 minus 2/5. I mean, 1 to any power is 1, so I really don't need to write 1 to the 5/2. Minus, then we plug in 0, and 2 times 0 to the 3/2 is 0, minus 2/5 times 0 to the 5/2 is also 0. So I end up with 2 times 1 minus 2/5. Or 10/5 minus 2/5 is 8/5. I think this is nicer than getting to this point and then plugging back in that u is equal to 3 minus x and saying I have 2 times 3 minus x to the 3/2 minus 2/5 times 3 minus x to the 5/2, and then plugging in x equal to 3 and x equal to 2. That just seems like a giant pain. So I wouldn't do it that way. Interesting. Okay. Additionally, that would make it wrong because I did some flipping of order, so I would need to be extra careful there. Yeah. All right. So I think that's maybe not. That's a good amount of problems where we do definite intervals like that. I know there were some requests for some other crazy problems on the homework. Let me take a look at these crazy ones. So yeah, we kind of, oof, God, yeah, that one. Okay, let's look at this one because it looks awful, but it's really not that bad. And I feel like I should change it up just a little bit. So I'm gonna look at problem 41, which looks atrocious. And how do I want to modify this? Yeah, okay, let's do that. Let's do the integral of, this is gonna be gross. I don't know that, yeah, I might have to actually just look at this one as is. You guys are like, that's not a problem. Secant squared of, okay, e to the square root of 5x plus 3. I'm going to change that 3 to a 4, make it feel like I'm doing a different problem. That's a lie I'm telling myself. Over the square root of x e to the negative square root of 5x. This is problem 41, or this is similar to problem 41 on the web work. And that looks pretty heinous. I'm not, yeah, that's, so this is one of the things that's true about integration in general, is that sometimes you have to guess. And sometimes you're going to guess wrong, and you're going to do some work, and then you're going to have to start over. And if I had to guess, you don't tell me, yeah. So this is where we're going to go back to our methods for guessing. You're going to guess something that's stuck inside another function. I think there are 2 plausible choices here. I don't actually know because I haven't done this problem. I think you could choose this for u. feel like that's not really going to get me what I want, but it might. Or I could also choose everything inside the secant squared function. Those both seem like reasonable choices for you. And even though I think it's going to be the green one, I'm not actually sure. Since I'm not actually sure, I should probably try and do less work if I think it's going to go maybe not right. So I'm going to try letting u equal e to the square root of 5x. And my du, okay, what's the derivative of e to the square root of 5x? That's a good question. So remember, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of the square root of 5x, okay, that's 5x to the 1/2. The derivative of that is 1/2 times 5x to the negative 1/2 times the derivative of the inside part, which is 5. And I can rewrite this as 5 over 2 times the square root of 5x. Maybe not in parentheses, right? Technically here in this particular problem, I haven't chosen the thing that is just in parentheses, right? I chose the thing that was the square root of 5x, and that's just in the exponent of e, but in this problem, it's actually not written explicitly in its own parentheses. It can be the stuff that's just inside a root, right? That would also be a choice that we made like in the previous problem, right? This 3 minus x wasn't in parentheses. It was definitely the right choice. But looking in the parentheses is a good place to look. It is often the choice for you, but not always necessarily. I don't even know if this is right yet. So let's see. So my du is e to the square root of 5x times this, which we found was that, times 5 over 2 root 5x dx. Wow. And I think we might have gotten lucky here. Maybe not. Maybe this is a garbage fire. I think I made the wrong choice, but let's take a look and see. Yeah, I'm pretty sure I did. So here's what I see. I see, man, I see hot trash is what I see. Whew. All right, so here's what I see. I see that this is, so e to the square root of 5x is 1 over e to the negative square root of 5x. I'm actually getting that term there. So this is 1 over e to the negative square root of 5x times, I can break this up. This is 5 over 2 times, the square root of 5x is the square root of 5 times the square root of x dx. 5 over root 5 is just root 5. So look, I've kind of got almost everything I need. I've got the square root of x, and I've got e to the negative root 5x. So I'm running out of room. Here's what I've got. I've got that du is equal to 1 over e to the negative root 5x times 2 times root x, all in the denominator. I don't want that 2 though. So I'm going to multiply the 2 over here and say 2 du, sorry, 2 du, so I don't have this 2 anymore, is equal to 1 over root x times e to the negative root 5x. Come on. Dx. Okay, this isn't going to work, but it is helpful anyway. So here's what we're going to end up getting. Dx times 1 over the root square root of x e to the negative root 5x. That's all of that. That's dx over root x e to the negative root 5x. So what we can say is our integral is equal to, so this whole thing I just circled, I can replace with a 2du. And then I'm left with secant squared of e to the u plus 4. Right, replacing the square root of 5x with a u. Now here's the problem, and I probably should have thought about this ahead of time, but I was just trying to make a good choice for you. The problem I have is that I don't know how to integrate secant squared of e to the u plus 4. So what do we do about that? Well, it means we probably needed to make a different choice. But this work we did here is still going to be helpful. So let's do it again. Well, let's do it differently. So now we are going to make the choice that Sophia suggested, is that it's all the stuff inside the parentheses, which I will also reiterate is usually a good guess. It's not always right, but I think in this case it is. This problem is pretty heinous, I'm not going to lie. Okay, so here we are looking at this problem again. So it's the integral of secant squared of e to the square root of 5x plus 4 over the square root of x times e to the negative square root of 5x. I feel like it's almost dumb to write that e to the negative square root of 5x down there. A normal person, a person writing this problem who wasn't a cruel, so this, not that I'm saying your professors are cruel because they didn't write this problem. I would actually rewrite my integral with the square root of x on the bottom and this e to the positive square root of 5x on top. That just makes a little bit more sense to me. Cool. So then we're going to make the other choice. So we're going to try letting u equal not just the square root of 5. Oh my God, am I an idiot? Wow, I'm done. That's okay. I did the thing I said we shouldn't do. We can fix it though. So here's the thing I did that was kind of, no. Oh, wow, I'm really sorry. So I made a mistake. It's not a huge deal and we can fix it. We don't have to do all this work. So here's the mistake I made in case you guys didn't notice, and that's all right. I said I was going to pick u equal to the square root of 5x. And then I picked u equal to e to the square root of 5x, right? Here's the nice thing. That was almost the right choice. And in fact, we can fix it by adding on 4. Because adding on 4 doesn't change any of the derivative stuff we just did. So we've actually got that this is equal to not secant squared of e to the u, right? Because I didn't choose u equal to this. I chose u equal to that. So it's really secant squared of u plus 4, but then I threw on the plus 4, so it's really the secant squared of u. So we're actually getting something we do know how to anti-differentiate. So again, I apologize because I said I was making a choice and it actually made a different choice. I think my brain just decided that it knew what we're supposed to be doing. So we're actually just getting secant squared of u. And we know how to anti-differentiate secant squared of u. It's just tangent of u. So here's what we get. After all this work, we end up with 2 times tangent of u, which is 2 times tangent of e to the square root of 5x plus 4. That's terrible. Let's pretend, maybe not pretend. Oh, don't forget the plus c. Let's say that we weren't thoroughly convinced that this was correct, because I could see after doing all this work feeling like it would have been really easy to make a mistake somewhere. We can check this by finding the derivative. Let's go to the other side. So we said our answer was 2 times tangent of e to the square root of 5x plus 4. I'm going to take the derivative just to see if I actually did it right. I mean, we can also plug our answer into WebWork or WebAssign and see if we did it right. Right, that is also a way to go. But let's find the derivative. So the derivative of 2 times tangent of e to the square root of 5x plus 4 is 2 times the derivative tangent of some stuff is secant squared of the stuff. So secant squared of e to the square root of 5x plus 4 times the derivative of the insides here, and the derivative of e to the square root of 5x plus 4 is, well, the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And the derivative of the square root of 5x we already did. I'm going to show it over here. Right, the derivative of the square root of 5x is exactly this. It's 1/2 times 5x to the negative 1/2 times 5. And now let's check out what happens. The 2 and the 1/2 cancel. I feel like I'm off by something here. Because, yeah. So I've got secant squared of e to the square root of 5x plus 4. I can bring this down to the bottom and say it's divided by e to the negative square root of 5x. This here is 5x to the negative 1/2, which is 5 to the negative 1/2 times x to the negative 1/2. X to the negative 1/2 is 1 over the square root of x. So I can have a square root of x down here. And then I still have a 5 to the negative 1/2 times a 5. And that's going to be the square root of 5. So it looks like my answer is off by a factor of a square root of 5. Yeah, I'm definitely going to flip it again. Oh, and it totally is, right? I had the square root of 5 here, and I totally lost it when I was doing when I was rewriting it up here. So there should have been losing my mind. There should have been a square root of 5 somewhere in either the new. Well, let's see. Let's go back and actually look at our answer or our result. We have a multiple of root 5 too much. So we actually needed to be dividing by root 5 to have it work out correctly. Yeah, so that's an excellent question. What time is it? 2:55. So here's how we wanted to go about solving this. Yeah, I'm going to erase this. So what we should have done here is we should have let u equal e to the square root of 5x plus 4. Our derivative, our du, is complicated. It is e to the square root of 5x times the derivative of that, which is 1/2 5x to the negative 1/2 times 5. This part here is kind of gross, right? This simplifies as e to the square root of 5x. I'm going to multiply both sides by 2. And then 5x to the 1/2 is, sorry, to the negative 1/2 is 5 to the negative 1/2 times x to the negative 1/2 times 5 to the first dx. X to the negative 1/2 is like multiplying by 1 over the square root of x. I can bring it down to the bottom as x to the 1/2, and then it's square root of x. So I have 2 du equal to e to the square root of 5x over the square root of x. And then I still have this 5 to the negative 1/2 times 5 to the first, which is 5 to the 1/2, or if you prefer, it's the square root of 5. I don't really want that either. So what I'm going to say, and this is where, oh, don't forget the dx, is I'm going to divide by that as well. So 2 over root 5 du is equal to e to the square root of 5x over the square root of x. dx. So here's what we're doing. We are replacing all of this garbage with 2 over square root of 5 du. I agree. Sorry, I know we got a little in the weeds on this problem, and I totally take the blame for that. So here's what we get. This whole thing I circled in green is just this whole thing I circled in green. I'm going to bring the constant multiply in front. So it's 2 over root 5 integral of du. And then I'm left with secant squared of u. And now it's not so terrible, I think. Right? This is 2 over root 5. And the antiderivative of secant squared of u is tangent of u. Plus c. And then we would plug back in that, which I'm probably not having enough room for. But this, our final answer, would be 2 over root 5 times tangent of e to the square root of 5x plus 4 plus c.